Hello AP Chemistry students, this is bond polarity in Chapter 8, and we're going to be talking today about covalent bonds. And so let's get right to it here. We know from regular chemistry that a covalent bond is when you have a nonmetal and a nonmetal, or nonmetals. This is not a solid, that's just more than one nonmetals. It's like carbon dioxide. We'd have covalent bonding occurring here, and basically in covalent bonding we're going to be sharing electrons, and we remember this from regular chemistry, hopefully. Now, when we have a couple different types of covalent bonds, and the first type of covalent bonds we're going to talk about is what's called a nonpolar covalent bond. And in a nonpolar bond, which is known shortly as just a nonpolar bond or nonpolar covalent bond, we have equal sharing of electrons. And this is going to be found in diatomics. So scroll down up a little bit. And so let's say we have a diatomic chlorine gas, and we were to draw the Lewis structure of this. This would be our chlorine molecules with a single bond and one single covalent bond in between the two. And these guys are going to share their electrons equally. There's not going to be any one chlorine that's going to pull those electrons closer to its nucleus than the other chlorine. And we'll talk about why that is here in a moment. But there are atoms, or molecules we should say, that have polar covalent bonds, or also known as just polar bonds for short. And these are guys that have unequal sharing of electrons. An example of this would be in the water molecule. And in the water molecule, oxygen does not like to share nicely. The oxygen pulls all the electrons close to it, and hydrogens are left a little bit electron deficient. And there's reasons for that, and we're going to talk about those next. The big reason why unequal sharing of electrons occurs is the idea of electronegativity. So let's scroll this down here. Electronegativity is the ability of an atom in a compound to attract electrons. So this is our big thing that we're going to be looking at. We kind of mentioned it a little bit in the video we had yesterday. The periodic trend that occurs for electronegativity is, here's our periodic table. As we go down the periodic table for electronegativity, electronegativity is going to decrease. And as we go to the right across the periodic table to the halogens, it's going to increase. So we would say fluorine is the most electronegative atom on the periodic table. It's going to be able to attract those electrons towards it. Sometimes we get in a bind where we have kind of a diagonal we're looking at on the periodic table. We're not sure, let's say, if nitrogen or sulfur, because they're on a diagonal, we're not sure which one of those two has the best or the most electronegativity, which is measured in what's called Paulings. You can always look on page 312 of your book. That's the white book, by the way. It might be off a little bit in the blue book. And that'll tell you the exact values of electronegativity so you can determine. So here's an example of an HF molecule. And in an HF molecule, if we were to draw, it would look just like this. We'd have a sharing of electrons, this single covalent bond occurring in the HF molecule. But what happens is because fluorine is so electronegative, it's going to actually attract all the electrons towards it, leaving hydrogen a little bit electron deficient. And because of this, we form a partial charge. And the way we illustrate a partial charge is we're going to put what's called a delta negative, because all the electrons are negative, are being pulled towards the fluorine, and a delta positive on the hydrogen. Now this has all kinds of implications that we're going to be talking about later. These hydrogen fluoride molecules are going to be attracted to each other because of slight charges, the same way water molecules are attracted to each other. So that's a talk for a different day. Just a thing that we want to note: the greater difference between the electronegativity of two atoms, the more polar their bond becomes. We just gave you a pretty extreme example of hydrogen and fluorine. Those guys are really far apart on the periodic table, so they're going to be a more polar bond. So here's a sample question. It says, which of the following is more polar, a BCl or a CCl bond? Both of them nonmetals. So the CLs are consistent, and so we just look at the periodic table for positioning. Boron is further to the left on the periodic table, so we would expect it to have a lower electronegativity, so this bond would be more polar than the other bond. carbon and chlorine are closer together on the periodic table, and so we wouldn't really expect for them to have the more polar bond. We could actually subtract the values too by looking them up on a table if we needed to. Last thing we're going to talk about is the idea called a dipole moment, and this is the quantitative measure of a magnitude of a dipole or a polar bond. So the charge that's on a molecule. So this is a dipole moment here. This is a little formula we'd use. Q is the charge differential that we talked about the other day, and R is just going to be the distance. So as the charge differential increases, greater charge, our dipole moment is going to increase as well. In nonpolar molecules, again, nonpolar molecules where equal sharing of electrons, we tend to say that they have zero dipole moments because there's no charge on those molecules. So dipole moments are kind of measuring the charge, the magnitude of the charge. Polarity measures the attraction of those electrons, how polar a bond is. Now that's a real quick run through on what we're talking about in chapter 8.4, and there's going to be some homework questions left up on the board. Hope you guys have a great day.